Hi everyone. So far this chapter we've been learning how to solve systems of equations, and we're going to keep working with what we know so far, but what we're going to be focusing on today is how to solve special types of linear systems, or really it's more about identifying special types of linear systems. And this should sound really familiar if you think back to when we were solving equations. Sometimes we had equations with no solutions or infinitely many solutions, and the same thing is going to be true for systems. So the first type of systems we're going to talk about is systems that have no solution, or they're what we call inconsistent. So when a linear system has no solutions, we say that the system is inconsistent. So that's really kind of a fancy word for saying that there's no solutions. So let's see what that would look like. So we're asked to solve the following system, and it's telling us to use elimination. Now the nice thing here, if we're going to use elimination, is that my x's are already on top of my x's, y's are on top of my y's, and my constants are all lined up. Now with elimination, I need the coefficients of one of the variables to be opposites. So if I look at the coefficient of x, here it's a positive 3 and here it's a positive 3. But really I need one of these to be a negative 3. And so I'm going to get that by just multiplying the second equation by negative 1. So my first equation is going to stay the same. 3x plus 2y is equal to 2. When I multiply by negative 1, on the bottom I'm going to get negative 3x. I'm going to distribute that negative, so I have a negative 2y. And over here, instead of a 10, I'm going to have a negative 10. Now, an interesting thing happens here. We notice that our 3x's are going to cancel out, but our y's also cancel out, which means really I'm left with 0 on this side, and then 2 minus 10 is a negative 8. Now looking at that, we know 0 is not equal to negative 8, right? We know that's false. So we would say this has no solution. We don't need to use the word inconsistent, we're just going to use the words no solution. And I'm going to make ourselves a note. We can recognize it's no solution when the variables drop out and we are left with a false statement. Okay, so that's one way where we're going to recognize that there's no solution. So let's look at example number 2. We're going to solve by graphing here. And let's see, right away I'm noticing there's an error here. Let's make this, it should not be an equal sign, let's make that a plus sign. So we have y equals negative 3 half x plus 1. So if I'm going to graph that, I know my y-intercept is a positive 1. My slope is negative 3 over 2, so that means I'm going to go down 3 and over 2. Okay, so I've got some points and I'm going to go ahead and draw in that line. I have to use my schedule or my ID here. Sorry about this. Alright, so there's my first line. Alright, so now I'm going to graph my second line. Here, my y-intercept is a positive 5. So I'm going to sketch that there. My slope is a negative 3 halves. So again, I'm going down 3 and over 2. Down 3 and over 2. And what I notice pretty quickly is those two lines are never going to intersect. Those are what we call parallel lines. So in this case, we have parallel lines. And we know those lines never intersect. So when that happens, we say there's no solution. Okay, so that's an example of how we're going to recognize when we have systems that have no solution. All right, next we're going to look at systems that have infinitely many solutions, and we call those dependent systems. So when a linear system has infinitely many solutions, we say that system is dependent. So let's see what this would look like. Now, in our first example, this says solve using substitution, which I can tell is going to be a good option here because y is already by itself. So it means I'm going to take this stuff that we know is equal to y and plug it in y's place. I'm going to replace y with that expression. So now I have x minus 2 times, well, this is 1/2 x plus 2, and then I get equals -4. So let's go ahead and do what we need to do to solve this. So I'm going to distribute my -2, and I'm going to get x, let's see, -2 times 1/2 is -1, so minus x. -2 times a positive 2 is a -4, and that's equal to -4. Now here I notice I have an x and then I have a -x. So those are going to cancel each other out and I'm left with -4 equals -4. So just like up here, my variables have dropped out, but instead of being left with a false statement, I have a true statement. So in this case, we would say infinitely many solutions. And you have to write out those words. Infinitely many solutions. Right? And we're going to know we have infinitely many solutions because the variables drop out. And we are left with in this case, a true statement. All right, in the next example, we're going to solve by graphing. So let's go ahead and I'm going to graph my first line here. My line is 1/2 x plus 2. So let's see, I go up 2. My slope is up 1 over 2. So I've got a bunch of points there. We'll go ahead and graph that line. So here's my first line. When I go to graph my second line, though, I notice that it's the same line. My y-intercept is the same and my slope is the same, so I end up graphing that same line. So really, those lines are really kind of on top of each other. They're the same line. So in this case, we have the lines end up on top of each other. So in that case, we would say we have infinitely many solutions. And again, you would need to write those words to show me that you know what it means when those lines are the same line, when they're on top of each other like that. All right, let's keep going. Now, the last type we have is what we call consistent systems. And this is really what we've seen so far. Sorry about that. When a linear system has just one, I guess we could say when it has exactly one solution, we say that the system is, it's not dependent, let's cross that off. We say it's consistent. And again, that's what we've been working with so far, when it has one solution. And so we have a note here. If we know that a system has one solution, we need to identify the solution. And in parentheses, I'm going to put the ordered pair. All right, so this is really what we've been working with this whole time. So let's go ahead and take a look. Let's see, for number 3, this is going to be a good candidate for substitution. Again, y is all by itself here, so I'm going to take that and replace the y. So now I'm going to have x plus 2 times, in parentheses, I'm going to replace y with 3x plus 2, and that's equal to 11. So now I need to solve for x. I'm going to distribute the 2. I have x plus, let's see, 2 times 3 is 6x. 2 times 2 is 4, and that's equal to 11. Now I'm going to combine my x and my positive 6x. I have 7x plus 4 is equal to 11. I'm going to finish up here by subtracting by 4. And now I'm going to divide by 7 and get x equals 1. Now remember, we're looking for an ordered pair here, which means an x and a y. So now I have to go back and find my y value. So all I'm going to do is take this x equals 1 and replace it in this equation. So now I have y equals 3 times, we just said x was 1, and then I have plus 2, which is going to give me a value of 5. So my solution is 1, 5. I have one solution, and I've identified that solution. All right, and then we can do the same thing by graphing. So quickly here, my first line, I have y equals 3x plus 2, which tells me my y-intercept is 2. My slope is 3 over 1, so I'm going to rise 3 and run 1. And I'm going to plot a bunch of points so it'll make it easier for me to identify the solution later. All right, and now for my second equation, I have to be a little careful here because I have decimals. So my y-intercept is 5.5, so I know I'm halfway between 5 and 6. My slope is negative 1 over 2, which means I'm going to go down 1 and over 2. Now I have to be careful. Going down 1 means now I'm in between 4 and 5. And I'm going to go over 2, which puts me right here. Down 1, over 2. And I've got some points, and it looks like I can see that intersection point right here. So now looking at my graph, I can see that my intersection point is right here, and that ordered pair is going to be 1, 2, 3, 4, 5. All right, so we're going to leave the video at that. When we're back in class, we'll go over some examples to make sure we understand the difference between all of these ideas, and then you'll have time to practice with that. See you back in class.